For 13 billion years, the vast universe has quietly kept a profound secret from us. It's as if some great cosmic architect placed a prohibition, forbidding us from accessing the true power of all things. For an immensely long time, we humans have lived in ignorance. We burned every branch, every lump of coal, completely unaware that right beneath our feet, in every tiny speck of dust, or in every cool drop of water, a vast and unimaginably huge ocean of energy lay locked away. The scientists who first laid hands on this secret in the early 20th century felt a vague sense of fear. They understood that they had just found the key to opening a mysterious Pandora's box. Mathematical formulas revealed something that seemed impossible. Matter was not merely the building material of the world, but a catastrophe of condensed and subtly preserved energy. So, who or what is holding this intense energy inside? Why don't the atoms around us spontaneously explode every second? And is it possible that the world we see is just a thin veil, stretched taut over a raging ocean of the quantum world? Tonight, let's try to break this code together. Let's begin our journey of investigation with the simplest yet most complex question. What is matter, really? Right now, you might be leaning back in a chair or holding a smartphone in your hand. You feel the weight of the device, sense the texture of its casing. Your finger glides across the screen without passing through the glass. To our brains, everything is clear. There are solid objects, and they occupy a specific place in space. This intuitive view of physics has served humanity faithfully for thousands of years. Since ancient Greece, the philosopher Democritus hypothesized that if we were to divide matter into smaller and smaller pieces, sooner or later we would encounter something that could no longer be divided, something both solid and eternal. He called it atomos. For a long time, scientists thought of the atom in just this way, viewing it as a tiny, incredibly hard sphere, like a microscopic billiard ball. This model was convenient, as it explained how gases mixed or how chemical reactions occurred. Even in the late 19th century, when physicists began to suspect that some electrical charges were hidden inside the atom, the overall picture of the world still appeared quite dense and stable. The most popular theory at the time was the model proposed by Joseph John Thomson. He had discovered the electron, the first subatomic particle, and understood that the atom was not, in fact, indivisible. But how were these electrons arranged? Thomson envisioned a model that the English-speaking world calls the plum pudding model. Imagine a positively charged mass, like a fuzzy sphere of charge, into which small, negatively charged electrons are sprinkled like raisins in a muffin. According to this idea, the atom was uniformly filled with matter. It seemed porous, but it was still a solid mass. Most people thought this way, until Ernest Rutherford entered the scene. The history of science has known many turning points, but what happened in Rutherford's laboratory in Manchester in 1909 could be called the moment humanity truly had its first awakening. Rutherford was not a dreamy theorist. He was an experimental genius, someone who always liked to get his hands on the true nature of reality. Together with his assistants, Hans Geiger and Ernest Marsden, he decided to test the durability of Thomson's model. The experiment was designed with incredible cleverness. They simply used a source of alpha particles. Alpha particles are heavy, positively charged bullets, ejected during radioactive decay. In essence, they are the nuclei of helium atoms. Although this wasn't known for certain at the time, they accelerated these particles to tremendous speeds and aimed them at an extremely thin gold foil. Gold was chosen not by chance, but because it is a very malleable metal. Rutherford was able to roll the gold foil so thin that it was only a few hundred atoms thick. The idea of the experiment was this: if the plum pudding model was correct, if the atom was indeed a spongy cloud of positive charge with light electrons interspersed, then the heavy and fast alpha particles should pass straight through this gold foil with almost no obstruction. Perhaps they would be deflected just a tiny bit, by a fraction of a degree, like a bullet passing through a thick fog. Geiger and Marsden sat in complete darkness, peering through a microscope at a special screen coated with zinc sulfide. Each time an alpha particle struck the screen, a tiny flash of light, a faint glimmer, would appear. They had to painstakingly count every single one of these flashes for hours on end. At first, everything went exactly as Thomson's theory predicted. Most of the particles flew straight through the foil, but then, Marsden noticed something incredibly strange. Some flashes were appearing in places where they shouldn't have been. Some particles were being deflected at very large angles, and then the unbelievable happened. Marsden ran to Rutherford and reported that about 1 in every 8,000 particles was bouncing straight back. It hit the gold foil and then reversed direction toward its original source. To help you understand the magnitude of Rutherford's shock, let me quote his own words. He said, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." I invite you to pause for a moment to reflect on this astonishing comparison. How could a massive naval artillery shell bounce off a flimsy piece of tissue paper? This is utterly impossible, unless that tissue paper is not just tissue paper. This could only happen in one scenario. If hidden inside that paper was something incredibly tiny, yet immensely heavy and solid, something the shell had hit head-on. Rutherford sat down, did the calculations, and realized an inescapable truth. The atom was nothing like a pudding. The entire positive charge and almost the entire mass of the atom, over 99.9% of it, was concentrated in an extremely tiny point at its center, the nucleus. Surrounding this nucleus, at a vast distance relative to its size, were the light electrons, flying about. But the most astounding part of Rutherford's discovery was its scale. The numbers he came up with are truly beyond normal comprehension. Let's try to visualize them together, because the human brain is notoriously bad at grasping abstract exponents. Imagine that an atom is magnified to the size of a giant football stadium, like Luzhniki or Wembley. We are standing in the stands, looking down. So, where is the nucleus? Perhaps you think it's the football placed in the center of the pitch? No, that would still be far too large. The nucleus of the atom, on the scale we are imagining, is just a tiny cherry sitting alone in the center of the grassy field. And what about the electrons? The electrons would be like tiny specks of dust, hovering somewhere in the highest rows of the stands, tracing out enormous orbits around this cherry. And what is between them? What lies between the cherry in the center of the stadium and those distant specks of dust in the stands? The answer is nothing. Absolutely nothing. It is emptiness. A vacuum. The atom is, in fact, empty. This is the most bewildering discovery in the entire history of material physics. Solid gold, heavy lead, or hard diamond, all of them are made of 99.99999% empty space. If we were to remove all the empty space from the bodies of every person on this earth, all 8 billion of us, and leave only the nuclei and electrons, pressing them tightly together, then all of humanity would fit into the volume of a single sugar cube. However, that bizarre sugar cube would weigh hundreds of millions of tons. At this point, a very reasonable question arises, one that is surely spinning in your mind right now. If the atom is mostly empty space, if it's just sparse specks of dust flying aimlessly in a vacuum, then why can't we walk through walls? Why, when I sit down on a chair, don't I fall right through it? Why does my finger feel resistance from the surface of the table? After all, in principle, emptiness should be able to pass through emptiness without any trouble, right? The answer to this mystery lies not in matter itself, but in force fields. The truth is, we never actually touch matter. When you press your finger against the tabletop, you are not feeling the atoms of the table. What you are feeling is electrostatic repulsion. The electrons in your fingers have a negative charge, and the electrons in the table also have a negative charge. From what we know from basic physics, like charges repel each other. As you bring your finger closer to the surface of the table, this repulsive force becomes even stronger. It increases dramatically at extremely tiny distances. What your brain is interpreting as solid is actually just a powerful electromagnetic field at work. You are actually hovering over your chair at a height of about 1/100 millionth of a centimeter, suspended on an invisible cushion of electric force. Throughout your life, you have never truly touched anything at all. But that's only half of the truth. There is another important factor that prevents matter from being compressed, which is a principle discovered by the Austrian physicist Wolfgang Pauli. It is called the Pauli exclusion principle. In the simplest terms, this quantum law states that certain particles, including electrons, are individualists to the extreme. Two electrons can never be in the same state, at the same location. They absolutely hate being crowded. When you try to compress an atom, the electrons begin to fall into a state of panic. They need their personal space to exist. The harder you squeeze them, the faster they move, creating an insane amount of resistance. This is called degeneracy pressure. It is this quantum fussiness of electrons that gives matter its volume, preventing atoms from collapsing into a single point. Therefore, the world we live in is essentially a grand illusion. The solidity we see is just the manifestation of interacting forces within empty space. However, let's get back to Rutherford and his model. The planetary model of the atom that he proposed, with the nucleus acting as the sun and the electrons as planets, had a fatal flaw. According to the laws of classical electrodynamics, any accelerating charged particle and moving in a circle is always an accelerating motion, must radiate energy. This means that an electron, as it orbits the nucleus, would have to constantly lose energy by emitting light, and very quickly, within a fraction of a nanosecond, it would have to break and fall directly into the nucleus. If that were the case, all the atoms in the universe should have collapsed immediately after they were created. Matter should not be able to exist. But the truth is, we are still here. Atoms are incredibly stable. The gold in the ring on your finger has remained gold for billions of years. That means that, inside the tiny atomic world, completely different laws are at work. Laws that forbid the electron from falling into the nucleus. And it is here that the magic of the quantum world truly begins to unfold before our eyes. Niels Bohr, a brilliant student of Rutherford's, came up with an incredibly bold idea. He suggested that electrons can only travel in certain, very strictly defined orbits. When in those orbits, the electron seems to become invisible to the laws of classical physics. It doesn't radiate any energy. It can only jump from one orbit to another by emitting or absorbing a tiny particle of light called a photon. Later on, with the development of quantum mechanics, the picture of the atom became more mystical and surreal than ever before. Scientists Werner Heisenberg and Erwin Schrödinger showed that the electron is not at all a tiny ball flying around, as we had always imagined. Instead, it is like a wave of probability, a fuzzy cloud enveloping the nucleus. The electron is now present everywhere, and yet at no specific place at all. The atom no longer resembles an easy-to-understand solar system, but has transformed into a constantly vibrating and oscillating mass of probability. But now, let's pause for a moment to look back at the first chapter of this journey of discovery. We have discovered that the atom is actually a vast, empty space, at the very center of which lies a tiny but incredibly heavy nucleus. Everything that we have always considered reality is, in fact, just the silent interactions of electromagnetic fields taking place at the edge of that empty space. However, the key issue lies here. If the electrons are so light and so far away, it means that the entire mass, the entire weight of matter, is concentrated in the nucleus, that tiny little cherry in the middle of the huge stadium we envisioned. To truly understand why such a great source of energy is hidden inside every atom, we need to temporarily forget about those electrons. They are just like the light outer shell, or like a thin candy wrapper on the outside. Because the most interesting, the most frightening, and also the most powerful thing is hidden deep inside the center. Let's step down from the stadium bleachers together, walk across the vast empty field to look closely at that cherry. It is there, in that tiny nucleus, that Mother Nature has hidden her greatest secret. And this is a secret that completely contradicts everything we have always known through common sense. Inside the nucleus are protons, particles that carry a positive charge. We all know that like charges repel each other, and this electrical repulsion is truly a terrifying force. If you try to take two protons and bring them very close together at the distance within an atomic nucleus, the repulsion between them becomes extremely fierce. So, why doesn't the nucleus get blown apart into countless tiny pieces? What force can hold a group of particles that bitterly hate each other, always trying to fly away from each other at the speed of light, so tightly bound together? At this point, we are gradually approaching the boundary of the world that humanity has always understood. To understand what force is holding the nucleus steady, we will be introduced to a type of force that humans didn't even know existed until the 20th century. It is a force so strong that, compared to it, the gravitational force holding the planets together is as gentle and weak as a passing breeze. A few moments ago, we stopped right at the threshold of the atomic nucleus. We imagined ourselves stepping down from the stands of a large stadium, walking across the empty field to get closer to the tiny cherry in the center. And right here, as we immerse ourselves in looking at that tiny point, anyone who has ever heard of basic physics would have to exclaim in amazement, "This is truly impossible." Let's find the answer to the question. Why is the existence of the atomic nucleus such a blatant violation of order, a true rebellion against the simple laws of electricity? As we know, the nucleus is made up of protons and neutrons. Neutrons, true to their name, are always electrically neutral and carry no charge. In a sense, they are like the peacekeepers. However, protons carry a positive charge, and Coulomb's law of electric charge is an unshakable truth. Like charges, always repel each other, and the strength of that repulsion depends entirely on the distance between them. The closer the charged particles are, the more strongly they want to push each other away. If you've ever tried to bring two strong magnets with the same poles close together, you probably still remember that springy feeling of resistance. The harder you try to push, the more some invisible force pushes your hand away. Now, imagine that we are trying to bring two protons very close together. When they are at a distance equivalent to the size of an atomic nucleus, which is about 1/10 trillionth of a centimeter, how terrifying would that repulsive force become? If we could scale this situation up and imagine that the two protons were the size of 2 billiard balls, the repulsive force between them would then be equivalent to the weight of an entire massive mountain. Just imagine two tiny spheres, and between them rages a storm, so powerful it could tear through thick steel plates as if ripping a thin piece of paper. And yet, the miracle is that in the nucleus of every atom that makes up your body, or in every atom of air that you breathe every day, there are dozens, even hundreds, of such protons sitting right next to each other. They are enclosed and held tightly in an extremely cramped space without being flung apart. This is truly a great paradox. If only gravity and electromagnetism existed in this vast universe, there certainly could not be any kind of matter more complex than the element hydrogen. Any nucleus containing 2 or more protons would immediately explode from within under the tremendous pressure of their own charge. But nuclei are stable, which means there must be something else. A third force must be present. There must be some colossal force, an invisible hand capable of holding these frantic protons together and forcing them to stay, despite their wild desire to flee from one another. Physicists in the early 20th century were forced to acknowledge the existence of this force. Although it was a completely new concept, it was given a rather unimaginative name: the strong nuclear interaction, or as we often call it, simply a strong force. This name is no exaggeration. The strong interaction is the most powerful force we know of in the entire universe. To give you a better sense of its scale, this force is about 100 times stronger than the electromagnetic force that pushes protons apart, and it's 10 to the 38th power, that is, about 100 undecillion times stronger than gravity. If gravity were a faint whisper, the strong interaction would be the deafening roar of a jet engine. But if this force is so powerful, why don't we notice it in our daily lives? Why doesn't it suck my cup to the table or pull my body into the wall? And finally, why doesn't it compress the entire universe into a single, gigantic mass? The answer lies in their range of operation. Each type of force has its own distinct limits. Gravity and electromagnetism are very long-range forces. Their influence can extend to infinity, though it weakens with distance. For instance, the Sun's gravity can still hold onto Pluto from billions of kilometers away. In contrast, the strong interaction is a force with an extremely short reach. It can only exert its effect over distances comparable to the size of the atomic nucleus itself. That distance is about 1 femtometer, which is 1/millionth of a billionth of a meter. As soon as particles are even slightly farther apart than this fragile distance, the grip of the strong interaction instantly vanishes, dropping to zero. You can imagine this force like a piece of Velcro or an extremely powerful magnet wrapped in a thick layer of foam. As long as you don't press the two pieces firmly together, nothing happens. But once they touch, it's nearly impossible to pull them apart. Or, try to picture two sumo wrestlers locked in a hold. They are holding each other incredibly tightly, but for this hold to work, they must be pressed right up against one another. If they stood just a meter apart, they simply couldn't reach each other anymore. That is why, deep inside the tiny nucleus, a perpetual battle between giants is always taking place. On one hand, the electric force, or Coulomb's law, is trying to tear the nucleus to shreds, pushing the protons apart. On the other hand, the strong interaction acts as a kind of superglue, pulling all the particles inside the nucleus into a stable, unified whole. But how exactly does this magical glue work? The mechanism of the strong interaction was a puzzle for a long time. In the 1930s, the Japanese theoretical physicist Hideki Yukawa proposed a theory that was both elegant and audacious. He asked himself, how does one particle know another is nearby to attract it? In the strange quantum world, forces don't just act mysteriously across empty space. Every interaction is an exchange. Imagine two people on ice skates. If one person throws a heavy ball to the other and the other catches it, both will be pushed apart by the recoil. This is a great analogy to explain a repulsive force, but how can we explain an attractive force through an exchange? Here, the analogy becomes a bit more complex. Imagine two people trying to snatch the same object from each other's hands. They constantly pass it back and forth, neither wanting to let go. It is this continuous tug-of-war exchange that links them, keeping them right next to each other. Yukawa hypothesized that protons and neutrons in the nucleus are constantly throwing special, intermediary particles to each other. Yukawa even calculated the mass of this hypothetical particle. It had to be heavier than an electron, but lighter than a proton. Therefore, He called it the mesotron, a name that was later changed to meson, from a Greek word meaning in the middle. That was truly a brilliant prediction. Yukawa described a particle that no one had ever seen, based only on the idea that the nucleus had to be held together by something, and a few years later, in 1947, the physicist Cecil Powell actually discovered this particle in cosmic rays, and it was named the pi meson or pion. The picture now became clearer and more vivid than ever. Inside the atomic nucleus, life is incredibly bustling. Protons and neutrons aren't just sitting there like marbles in a bag, they are constantly exchanging pions at a frantic pace. A proton emits a pion and, for an instant, becomes a neutron. A neighboring neutron immediately catches that particle and transforms into a proton. This non-stop game of catch happens in the blink of an eye, and it is this constant exchange that creates the extremely powerful field of force we call the strong interaction. Now, let's talk about the role of neutrons. So, what are they really needed for? Why didn't nature just create a nucleus made entirely of protons? Remember the battle of giants we just mentioned. The electric repulsion acts between all protons inside the nucleus. Every single proton is trying to push all the other protons away. The more protons there are, the more intense and ferocious this storm of electrical repulsion becomes. However, the strong interaction, as we know, has an incredibly short range. A proton can only embrace and attract its immediate neighbors, the particles that are actually touching its surface. It absolutely cannot reach its arm out to another proton on the other side of a large nucleus. It is at this point that a dangerous situation begins to arise. In large nuclei, the repulsive electric force continues to accumulate and multiply, while the attractive strong force cannot reach that far. If we just kept adding more protons, the nucleus would very quickly become unstable and shatter into pieces. And this is where neutrons come in. You could consider the neutron a brilliant and benevolent invention of Mother Nature. They also participate in the strong interaction game. They also have the ability to stick. But the wonderful thing is, they are completely neutral in charge. They don't repel each other, and they don't repel protons. By introducing more neutrons into the nucleus, nature seems to be trying to dilute that tense positive charge, helping to increase the distance between protons, while at the same time adding another layer of incredibly strong adhesive. You could say the neutron is the special cement of the nucleus. The heavier an element is, the more neutron cement it needs to hold its cumbersome structure together. For example, in a light helium nucleus, we see 2 neutrons accompanying 2 protons. However, in the heavy element uranium, with its 92 protons, we need more than 140 neutrons to bind that massive structure together into one piece. However, even this brilliant cement is not all-powerful. The strong interaction is, in fact, an incredibly delicate and sensitive balance. And it is this magical balance that leads us to the very heart of the question: where does the enormous energy inside the atom truly come from? Try to recall the feeling of stretching a rubber band or squeezing a spring in your palm. To do that, you had to do work to stretch or compress it. Inside that spring, potential energy was quietly stored. As soon as you let go, it will immediately spring back with force. The nucleus of an atom is actually just like a compressed spring, but in the opposite direction. Because the strong force is an attractive force, energy is released when the particles come together. To break a nucleus apart, we need to expend a huge amount of energy to stretch that binding spring. This also means that as long as the nucleus is intact and stable, this energy doesn't seem to exist in the system because it has been fully used to bind the particles together. Sounds a bit confusing, doesn't it? Well, let's try another comparison. Imagine that protons and neutrons are like extremely powerful magnets. When they snap together, you'll hear a loud click. In that very moment, they connect. A burst of energy is released, and can do work. For example, when they pinch your finger, and to pull them apart afterward, you'll definitely have to put in a lot of effort and break a sweat. The energy that holds atomic nuclei together is called binding energy, and the scale of this energy is so immense it's almost impossible for an ordinary person to comprehend. Let's make a comparison. All the energy humanity has used over the centuries, from the warmth of campfires and the power of gunpowder to the gasoline burning in powerful engines, all of it is just chemical energy. A chemical reaction is really just a rearrangement of electron shells. Electrons jump from one orbit to another, or change their bonding partners. The energy of these gentle bonds is measured in electron volts. When a carbon atom burns in a campfire, it releases only a few electron volts of energy. But now, look deep inside the nucleus. The binding energy of the particles within the nucleus is measured not in single units, but in millions of electron volts. This is a million-fold difference. When you burn a kilogram of coal, you're getting energy from chemical bonds. But when a nuclear reactor operates, it harnesses energy from the nuclear bonds themselves. This is why a tiny, pill-sized piece of uranium can hold the same amount of energy as a ton of coal or a full tanker of oil. Because the spring, hidden inside the nucleus, is millions of times stronger than the tiny springs holding atoms together in molecules. We tend to think of nuclear energy as something artificial, created by scientists in white lab coats. But in fact, it is the most fundamental and primordial energy of matter. The strong interaction is what keeps our world from disintegrating into dust. Without this force, there would be no carbon for life, no oxygen to breathe, and no iron in our blood. The universe would just be a homogeneous and incredibly boring cloud of hydrogen. However, an even more astonishing discovery awaited physicists when they decided not just to calculate this energy in theory, but to literally weigh it by putting a nucleus on a real scale. In the 1920s, the British physicist Francis Aston built a remarkable device called a mass spectrograph. This instrument allowed him to measure the mass of atoms with incredible precision. Aston began to weigh different elements and their nuclei, and in doing so, he discovered something that completely contradicted conventional arithmetic. Imagine you're at the grocery store. You buy 2 apples, each weighing 200 grams, and 2 pears, also weighing 200 grams each. You put them all into a bag. Logically, the total weight in the bag should be 800 grams, ignoring the negligible weight of the bag itself. 1 plus 1 equals 2. It's the most basic rule there is. Yet, in the world of nuclear physics, 1 plus 1 never equals 2. Aston found that if you take 2 separate protons and 2 separate neutrons and add up their masses, you get a value we can call A. But if you then take a complete helium nucleus, which is made of those very same 2 protons and 2 neutrons, and put it on the scale, the result is lighter than A. So where did that mass disappear to? A piece of matter had actually disappeared, vanishing into thin air during the very process of the nucleus being assembled. The difference wasn't enormous, less than 1%, but for the world of physics, it was a catastrophe, a profound shock. The law of conservation of mass, considered an unshakable truth since the days of the brilliant scientists Lomonosov and Lavoisier, was beginning to show cracks at its very foundation. This mysterious phenomenon is called the mass defect. It might sound like a flaw in nature's production line, but in reality, it's the golden key to understanding how the sun blazes, or how nuclear power plants generate electricity. Where did the mass go when protons and neutrons came together? And how was this loss connected to the incredible energy of the strong force we just talked about? The answer to this vexing question had, in fact, already been written down. It was contained in the most famous formula in the history of science, published by a humble patent office clerk decades before Aston's experiments. But at the time, no one could have imagined that this formula held the code to both our doomsday and our salvation. In the next chapter, we'll talk about how mass miraculously transforms into energy, why this weight loss in particles results in the release of immense heat. We'll analyze the very equation you've probably seen 1,000 times on t-shirts and souvenirs, but whose deep and rather frightening meaning you may have never truly considered. Let's start by diving into this grand equation, continuing our journey to uncover the deepest secrets of matter. In the first 2 chapters, we learned that the atom is almost entirely empty space, and its nucleus is held together by an incredibly strong force, the strong nuclear interaction. But so far, this all just sounds like beautiful theories about forces, fields, and particle exchanges, nothing you can really hold in your hand. However, science demands absolute precision, and a true breakthrough in understanding the nature of energy came not when physicists were lost in theoretical dreams, but when they decided to do a seemingly tedious job: accounting. They decided to weigh an atom. For a very long time, the law of conservation of mass had reigned supreme in the scientific world. It was established by some of the greatest minds of the past, like Mikhail Lomonosov and Antoine Lavoisier. Its principle is incredibly simple and intuitive. Matter is neither created nor destroyed. If you burn a log in a fireplace and then carefully collect all the resulting ash, smoke, and water vapor, their total mass will be exactly equal to the mass of the original log, plus the mass of the oxygen consumed in the fire. Mass was a constant, a stable anchor holding our reality in place. But in the early 20th century, overshadowed by noisy theoretical debates, there was a man obsessed with absolute precision in measurement. His name was Francis Aston. He was a student of J.J. Thomson, the man who discovered the electron. Aston was a talented engineer and a brilliant experimentalist. In 1919, at the Cavendish Laboratory in Cambridge, he created an instrument that would completely change the face of physics: the mass spectrograph. Let's take a look at how this machine works, because its principle is both brilliant and remarkably simple. Imagine you have a mix of ping-pong balls and golf balls. They look to be the same size, but their weights are completely different. How can you separate them without having to pick each one up by hand? One clever way is to roll them all down a ramp and at the bottom have a powerful fan blowing across their path from the side. The light ping-pong balls would be easily blown aside by the current of air, their paths bending a great deal. Meanwhile, the heavy golf balls would continue on, their paths barely altered. Ultimately, they would land in different bins at different locations. Aston's mass spectrograph operated on a similar principle. Instead of balls, he used ionized atoms, and instead of a fan, he used a powerful magnetic field. Aston accelerated atoms using an electric field and shocked them into a magnetic chamber. The magnetic force bent the atoms' trajectories. The heavier atoms would curve reluctantly along a wide, shallow arc. The lighter atoms, on the other hand, would be deflected sharply. At the end of their paths, they would hit a photographic plate, leaving distinct marks. By looking at the position of these marks, scientists could calculate the mass of the atoms with incredible precision. First, Aston confirmed the existence of isotopes. It turned out that an element like neon, for instance, has siblings atoms that are chemically identical but have different masses, such as neon-20 and neon-22. This alone was a major discovery, but the real shock was still ahead. Aston decided to re-examine the arithmetic of the nucleus itself. At that time, physicists knew that the nucleus was made of protons and neutrons. Although the neutron would only be officially discovered a short time later, its existence was already implied as part of the existing mass. Let's conduct a thought experiment to replicate Aston's exact logic. Imagine you have a model kit of the universe. In our hands, we have the pieces: 2 protons and 2 neutrons. We proceed to weigh them individually with the highest possible precision. Then, record their total mass in a notebook. Let's call this number A. Then, we take these pieces and bind them tightly together using the strong nuclear force. When we do, we get a complete helium nucleus, also known as an alpha particle. Now, we place this complete nucleus on Aston's mass spectrograph and we get a result we'll call number B. According to all the normal logic of this world, shouldn't number A be exactly equal to number B? Shouldn't the sum of the constituent parts be equal to the whole? The weight of a sandwich must surely be equal to the weight of the bread, plus the butter and sausage inside. However, Aston's mass spectrograph produced an unbelievable result. Number B turned out to be smaller than number A. The complete helium nucleus weighed less than the sum of its constituent parts. This difference was about 0.7%. It might sound like a tiny, insignificant error, but for the world of physics, it was a monumental disaster. Try to imagine something this strange. It's like you go to buy a kilogram of pure gold. You bring it home and melt it into a glittering gold bar, but the final result is only 993 grams. So, where did those 7 precious grams of gold disappear to? They certainly couldn't have just evaporated into thin air. Aston patiently checked and recalibrated his equipment many times, but there were absolutely no technical errors. This phenomenon is completely real in nature, and scientists call it the mass defect. This discovery carries a profoundly deep meaning. When an atomic nucleus is formed, a part of the matter has literally vanished from our tangible world. It dissolves, but as we recalled a few moments ago, the nucleus is always held together by an enormous binding energy. It was at this moment that the greatest minds began to connect all the events. Remember the image of protons and neutrons sticking together with immense force. When they combine, the system releases energy outward. The nucleus, as if breathing a sigh of relief, settles down and transitions into a more stable, durable state. That excess energy was pushed out into space. A strange picture gradually emerged before our eyes. As mass disappeared, energy immediately appeared. Could these two phenomena have an intimate connection? Could it be that the disappearing mass had transformed into the very same intense energy that flew out when the particles collided? Or, looking at it from another angle, could the missing mass be the price, the sacrifice the particles had to pay to be together forever? Essentially, Aston had discovered a shocking truth. Mass was not the fixed, eternal thing we always thought it was. Mass could simply vanish, and in the moment it vanished, something magnificent would truly happen. To better understand this terrifying scale, let's return to that small number of 0.7%. It seems like a trivial matter, doesn't it? But imagine if just 1 gram of matter vanished completely into nothingness. According to the theory of conversion, the disappearance of just that 1 gram of matter would release an amount of energy equivalent to the explosion of 20,000 tons of TNT. Aston, looking at his charts and experimental photographs, was horrified to realize where this could lead humanity. In his Nobel Prize acceptance speech in 1922, he uttered prophetic words: "If humanity could find a way to turn matter into energy, we would hold in our hands a power beyond our wildest dreams." But at the same time, he also issued a grave warning. If we were to initiate this process in an uncontrolled manner, we could accidentally blow up this green planet, turning it into a new, fiery star in the void. But how exactly did mass transform into energy? What exchange rate governed them? For example, how much energy is a kilogram of roadside pebbles worth? Despite his incredibly precise measurements, Aston lacked the crucial theoretical key to convert from the unit of grams to the unit of joules. Fortunately for the flow of science, and perhaps as a fateful arrangement for the geopolitics of the 20th century, that key had actually existed for some time. It had been lying quietly in libraries, within the pages of scientific journals for 15 long years, waiting for its moment. It was an equation that perhaps every student in the world today knows by heart, but whose true meaning very few truly grasp. We have reached the point where Einstein's dry, experimental data would meet the brilliant insight of Albert Einstein. In the next part, we will analyze the most famous formula of all time to understand why light is the key that unlocks the secret of mass and why the matter around us is actually just light that has been compressed incredibly tightly. You have surely seen this formula thousands of times. It appears on t-shirts, mugs, in textbooks, and even in entertainment comic books. E equals mc squared. This is the immortal symbol of genius. But let's be honest with each other. If you were to ask a random person on the street what each letter specifically means and why there's a squared calculation, perhaps very few could give a thorough answer. People usually just say, "Oh, that's the formula for making an atomic bomb." That is correct, but it's only a very small part of the truth. This equation is not simply an instruction manual for creating weapons. It is a fundamental law, a truth about the existence of this entire universe. It is the answer to the questions: why does the sun always shine so brightly? And why does mass exist in the world? Let's go back in time, back to 1905. At that time, the young Albert Einstein was working as a clerk at the patent office in the city of Bern. He had absolutely no access to modern laboratories, nor did he conduct any practical experiments with atomic nuclei. The only things he had were his pen, blank sheets of paper, and a boundless imagination. In that year, a year that history would later call the miracle year, he published 4 scientific papers that shook the intellectual world. One of them was dedicated to the special theory of relativity. Einstein posed a philosophical question to himself. Does energy itself have inertia? Or in other words, does it have mass? Imagine a flashlight floating in zero gravity. You turn it on, and the flashlight emits a brilliant beam of light. That light carries energy. Does that mean the flashlight became lighter after emitting light? Classical physics would certainly answer no, because light has no weight. But Einstein, with his unshakable relativistic logic, reached a shocking conclusion. Yes, the flashlight did indeed become lighter. When an object emits energy, it loses a corresponding amount of mass. And conversely, when it absorbs more energy, that object becomes heavier. The great formula was born from such thoughts. Let's analyze it in detail. On the left side of the equals sign is the letter E, representing energy, the force that makes all things move, heat up, and shine. On the right side is the letter M, representing mass, the measure of inertia, or simply put, the amount of existing matter. Previously, physicists always believed these were two completely separate entities, like length and temperature. You can't convert meters into degrees Celsius, but Einstein bravely declared, no, they are, in fact, one and the same. Mass is just a very dense, very concentrated form of energy, and energy is just mass that has been liquefied and released. However, the most interesting thing and the key to the entire equation lies in the third letter, C. That is the speed of light in a vacuum. Why does it appear here? What does the speed of light have to do with a lifeless stone lying on the road? In this formula, C acts as a magical conversion factor. Imagine you're visiting a country where the currency is extremely valuable. You just need to hand over a tiny coin equivalent to 1 gram of mass, and you'll get back a huge mountain of local currency, equivalent to joules of energy. The exchange rate here is the speed of light squared. Let's try to grasp the enormous scale of this number. The speed of light is about 300,000 kilometers per second. In meters, that's 300 million meters per second. Now, square that number, 300 million times 300 million. The result is a colossal number, followed by 16 zeros. That's 90 quadrillion units of energy in the International System of Measurement. This has a truly staggering implication. In just 1 kilogram of any kind of matter, whether it's pure gold, pure water, or even just river mud, lies 90 quadrillion joules of energy. Numbers with 16 zeros are indeed difficult for our brains to comprehend. So, let's try a more relatable example. The energy hidden inside just 1 kilogram of ordinary potatoes is enough to keep a kettle boiling continuously for 25 million years, or enough to power a large country like the United States for several months on end. So why don't we notice this energy every day? Why doesn't a potato just explode in our hands? It's because that immense energy is securely locked away in the state of mass. It's like frozen energy. To release it, we must destroy the very fundamental structure of matter. And here, we return to Einstein's discovery of the mysterious mass defect. Do you remember the 0.7% of mass that vanished when the helium nucleus was formed? Einstein found that loss, but didn't know how to price it. And it was Einstein who provided the final price tag. Einstein's equation fully explained where the mass went. It had completely transformed into binding energy, the terrifying force we talked about earlier. A small portion of the protons and neutrons had sacrificed themselves, turning into pure energy to become the eternal glue holding the nucleus together. That's also why breaking an atomic nucleus is so incredibly difficult. To separate a tightly bound nucleus back into its individual particles, we must return the exact energy it lost. We have to pump energy back in so it can transform back into mass. However, this equation also works in reverse, and this is the most terrifying part. If we have a heavy, unstable nucleus where the protons are struggling to stay bound together, just a gentle push from the outside can cause it to shatter into smaller, more stable fragments. In that very process of shattering, a portion of the mass becomes redundant, and it is instantly released into the environment in the form of intense heat and radiation. When Einstein penned this formula, he honestly wasn't thinking about building bombs or power plants. To him, it was simply the pure beauty of theoretical physics. He even doubted whether humans could ever verify it experimentally. In 1935, during an interview with a journalist, he likened the possibility of obtaining nuclear energy to shooting birds in the dark in a country where there are very few birds. The great theorist was a bit mistaken in his pessimism. He had underestimated the capabilities of brilliant experimentalists. While Einstein was busy writing formulas on a blackboard, elsewhere, scientists had begun to figure out how to crack the atomic nucleus. They were relentlessly searching for a way to activate the E equals mc squared formula in the real world. And finally, they found the ideal hammer to carry out the task of smashing the nucleus. That hammer was called the neutron. This was a particle with no electrical charge, discovered by James Chadwick. Because it's neutral, the neutron can easily penetrate the atomic shell without any resistance. It isn't repelled by electrical forces. It's like a perfect saboteur agent that can infiltrate deep into enemy headquarters. The stage was now set for one of the most dramatic and pivotal discoveries in human history. The location was the city of Berlin. The time was the late 30s, on the very eve of the outbreak of World War II. In the next part, we will see how chemists and physicists, sometimes unwittingly, broke the final seal of the atomic nucleus and unleashed the power of distant stars into our own world. In the late 1930s, the atmosphere in the scientific world was more feverish than ever. Everyone vaguely understood that something great was hidden inside the atom. But breaking the nucleus still seemed like an impossible task. Even the great Ernest Rutherford, the man who discovered the nucleus, had called the idea of getting energy from the atom moonshine shortly before he died. He believed we would always have to spend more energy to destroy a nucleus than what we could ever get back from it. But history has always loved its unexpected ironies. The discovery that completely refuted Rutherford's skepticism and forever changed the destiny of human civilization didn't happen in a modern, futuristic laboratory with giant machines. Instead, it took place on an ordinary lab bench, cluttered with glass flasks and chemical measuring tools. The main characters in this historical drama were the German chemist Otto Hahn and the Austrian physicist Lise Meitner. Their creative and harmonious collaboration had lasted for 30 long years. Hahn was a brilliant chemist, a master at separating pure chemical substances. Meitner, on the other hand, was a profound theorist, capable of understanding the deepest physical nature of processes. They were truly a perfect team. But unfortunately, the vortex of politics intervened. In 1938, Lise Meitner, a determined woman of Jewish descent, was forced to flee persecution by the Nazis. She managed to escape and moved to the distant country of Sweden with only a small suitcase in her hand. Meanwhile, Otto Hahn remained in Berlin. He continued his experiments with a young assistant named Fritz Strassmann. Despite the geographical distance, they still corresponded regularly with Meitner. In their discussions about their work's progress, Hahn and Strassmann conducted an experiment bombarding the element uranium with slow neutrons. You see, uranium is the heaviest element ever found in nature. Inside its nucleus are 92 protons and more than 140 neutrons. This is truly a colossal and extremely unstable structure, already struggling to maintain its shape. At the time, scientists expected that when a neutron entered the uranium nucleus, it would get stuck there. As a result, the nucleus would become even heavier, then transform into a completely new superuranic element. This sounded very logical. Like when you add another brick to a wall, that wall must certainly get bigger. However, in December of 1938, Hahn discovered something so strangely unbelievable in his test tube. After bombarding uranium, he found the presence of barium in it. For a chemist, this was a huge shock. Barium is a medium-weight element, and its nucleus contains a mere 56 protons. That number is only about half of uranium's. So where did the barium come from? This was as bizarre as firing a pistol at a giant watermelon, but instead of seeing a hole in the watermelon, you see two intact cantaloupes in front of you. Hahn was extremely puzzled. He wrote a letter to Meitner, full of skepticism. He wrote, "Our radium isotopes are behaving just like barium. Perhaps you can come up with some extraordinary explanation for this phenomenon? Because we ourselves understand that uranium can't just break apart into barium." Lise Meitner received this letter on Christmas Eve of that year. At the time, she was walking in a snow-covered forest near the city of Gothenburg with her nephew, the physicist Otto Frisch. They sat down together on a fallen log and began to draw diagrams in the snow. Meitner suddenly recalled the liquid drop model of the nucleus that had been proposed before. Imagine the uranium nucleus like a large drop of water. The surface tension, which is the strong nuclear force, is trying to keep the drop intact. But inside, the electrical repulsion between the protons is constantly screaming, always trying to tear the drop apart. The drop is now trembling violently. It has reached its breaking point. What happens when an extra neutron collides with that violently vibrating drop of water? It adds a new source of energy, causing extreme chaos. The water drop begins to oscillate wildly, stretching out and taking on the shape of a dumbbell. And at a certain moment, the waist between the two halves of the dumbbell becomes too fragile. The strong interaction, our great cosmic glue, no longer has enough strength to reach from one end of the dumbbell to the other, and this is when the electric force speaks up. Both halves of the nucleus now carry a positive charge, and they furiously push each other apart with tremendous force. The water drop is finally torn apart. The uranium nucleus now officially splits into two separate fragments, barium and krypton. Right there, In the middle of the winter forest, Meitner performed a calculation on a small piece of paper. She calculated the mass of the uranium nucleus and the mass of the newly formed fragments. And once again, just like in Aston's experiment, the mass numbers didn't add up. The resulting fragments were lighter than the original nucleus. This mass difference was about 1/5 the mass of a proton. When she plugged this value into Einstein's formula, E equals mc squared, Meitner got a staggering result: 200 million electron volts. That was the enormous amount of energy released from the decay of just a single atom. It was a truly immense number. Those fragments flew out at a terrifying speed, heating up the surrounding space. Meitner and Frisch understood everything. Hahn had indeed successfully split the atom, and nature's final seal had been broken. However, the most frightening discovery was still lurking ahead. Soon after, other physicists, including Enrico Fermi and Leo Szilard, realized another crucial detail. When a uranium nucleus undergoes fission, it doesn't just break into two large fragments. It also ejects smaller pieces, which are 2 or 3 free neutrons. Now remember, to split a uranium nucleus, we only need 1 neutron. We use one, but we get 2 or 3 new ones in return. These new neutrons can then collide with other neighboring uranium nuclei. Those nuclei will also split, releasing more energy and generating even more neutrons. And so, from one initial nucleus, we get 2, then 4, then 8, then 16. An exponential increase. A true energy avalanche had begun. This is the chain reaction. Leo Szilard, the Hungarian physicist who had first predicted the possibility of a chain reaction several years earlier, later recalled that when he conducted the experiment and saw the faint flashes of light on the screen, he understood that the world is heading for sorrow. That night, he couldn't sleep a wink. He knew for certain that if you gathered enough uranium in one place to reach what's called a critical mass, this avalanche would release all the energy contained in Einstein's formula in just a fraction of a second. Instead of slowly heating water over millions of years, that energy would explode instantaneously. It would be an explosion capable of igniting a small sun right here on our Earth. The discovery of nuclear fission occurred at what was perhaps the worst possible time in all of human history. War was looming on the horizon. Scientists on both sides of the ocean, whether in Nazi Germany or the United States, immediately recognized the enormous military potential of this phenomenon. The race to build atomic bombs began almost immediately after Hahn and Strassman's paper was widely published. But you know, nuclear fission doesn't just bring death and destruction, it also brings life. In 1942, in the city of Chicago, Enrico Fermi successfully built humanity's first nuclear reactor. He proved that the chain reaction could be controlled. We can make it proceed slowly, releasing heat gradually to power turbines. We have learned how to harness this great energy by breaking apart heavy nuclei. In essence, we are reusing the energy from the electric repulsion that was locked inside the nucleus billions of years ago at the very moment these elements were born from the explosions of distant supernovae. We have simply released a tightly compressed spring. However, Mother Nature still has a much more powerful energy source hidden away. It's an energy source that doesn't require us to split heavy things, but instead forces light things to fuse together. It is the complete opposite of fission, a process called nuclear fusion. This very process lights up the myriad stars twinkling in the night sky. It is what keeps our sun from ever going out. If fission gives us an energy source capable of destroying entire cities, nuclear fusion offers an energy capable of destroying entire planets. But at the same time, it also promises humanity a source of limitless electrical power. In our next segment, we will journey deep into the fiery heart of the sun to learn how the alchemists of the universe transform hydrogen into light. And we will also find the answer to why recreating this process here on Earth is even more difficult than building an atomic bomb. We will be talking about thermonuclear fusion. Just imagine, if you could travel back in time about 150 years and ask the greatest minds of that era why the sun is always shining, they would have been completely stumped. It was one of the most vexing mysteries of the 19th century. Let's try to picture the enormous scale of this problem. Our sun is a gigantic ball of fire. Its mass is about 330,000 times the mass of the Earth. Every single second, it radiates an unbelievably large amount of energy into space. In the 19th century, the only way humans knew to generate that much heat was through combustion. Lord Kelvin, a great physicist, once tried to do a calculation. He wondered, if the sun were made entirely of the best quality coal and burned under the most ideal conditions, how long could it burn? The answer he got was truly disappointing, a mere few thousand years. However, geologists and biologists had long known that our Earth was millions, even billions of years old. Ancient fossils and geological layers proved that the sun had been warming this planet for countless eons. So, coal was definitely not the right answer. Later, Kelvin proposed another idea: gravitational contraction. The sun is massive, and its own weight crushes down on itself, causing it to shrink and become hotter. However, this method could only provide energy for about 20 million years. Although it was better, this number was still far too short for the evolution of life. The scientific world at the time had truly hit a dead end. The sun's energy source remained a top secret until the mysterious structure of the atom was discovered. The final answer only came when physicists realized that the sun is not a conventional furnace at all. In fact, the sun is a gigantic nuclear reactor, but it operates in a completely different way from human nuclear power plants. Instead of splitting heavy uranium nuclei, the sun does the opposite. It forces light hydrogen nuclei to fuse together. This process is thermonuclear fusion, the highest form of alchemy in the entire universe. Let's take a deep look inside the core of this familiar star. In that place, hellish conditions prevail. The temperature reaches 15 million degrees. The pressure is hundreds of billions of times higher than the atmospheric pressure right here on our Earth. Matter here exists in a plasma state, a soup of nuclei and electrons completely torn apart from each other. The main ingredient of this soup is hydrogen. A hydrogen nucleus is actually just a single solitary proton. And this is where the most interesting part begins. We all know that protons carry a positive charge, and they absolutely hate each other. They constantly try to push each other away. To force them to fuse, we must overcome what is known as the Coulomb barrier. Imagine trying to crash two cars head-on, but there's an extremely powerful spring between them. You would have to accelerate those cars to an insane speed so that, through inertia, they could compress the spring and actually touch each other. At the center of the sun, temperature is the factor that plays the role of speed. The heat of 15 million degrees Celsius makes the protons move at enormous velocities. And yet, the strange thing is that even this incredible speed still wasn't enough. According to the laws of classical physics, these protons should have still bounced off each other, unable to get close enough for the strong force to take effect. If that were the case, the sun would have gone out a long time ago. And at this very moment, the magic of quantum mechanics once again takes the stage. A marvelous effect, discovered by George Gamow, came into play: the quantum tunneling effect. In the mysterious quantum world, a particle doesn't have a single, definite position. It's always a little fuzzy in space, and there is always an incredibly tiny probability that a proton, upon reaching the repulsive barrier, won't bounce back, but will instead leak right through it like a ghost passing through a wall. This is an extremely rare occurrence. For any specific proton, the chance of it fusing with another is minuscule. A proton could wander inside the sun's core for billions of years before it gets lucky enough to find a partner to pair up with. However, because the number of protons inside the Sun is so unimaginably large, these rare events still happen in enormous numbers every single second. When two protons finally manage to fuse, a complex chain of reactions begins, a process described in great detail by the physicist Hans Bethe. This is the proton-proton chain. First, two protons merge, and one of them immediately transforms into a neutron, simultaneously releasing a positron and a neutrino. The result of this process is the creation of deuterium, also known as heavy hydrogen. Then, this deuterium nucleus captures another proton to become a light isotope of helium, called helium-3. And finally, when two helium-3 nuclei collide, they create a stable nucleus of regular helium-4, while kicking two excess protons back into the plasma. The final result of this grand alchemical process is actually very simple. Four protons have transformed into a single helium nucleus. However, if we were to once again use Aston's mass spectrograph to weigh them, we would find that this helium nucleus weighs slightly less than the total mass of the original four protons. The mass defect we just mentioned in this reaction amounts to 0.7%. That tiny fraction of mass that seemingly vanished was actually converted into the immense, pure energy of light and heat. Just imagine, in every single second that passes, our Sun burns about 600 million tons of hydrogen, turning it into 596 million tons of helium. Thus, 4 million tons of matter have completely vanished every second, converted into the warm light that brings life to all species on our Earth. This nuclear fusion reaction is far more efficient than uranium fission. The energy released is many times greater, and the best part is that it leaves behind almost no toxic radioactive waste. For that reason, scientists have dreamed of building a miniature sun right here on Earth for over half a century. However, this has turned out to be an incredibly difficult and challenging task. The problem is how to contain the thermonuclear plasma, which has been heated to 100 million degrees. You see, here on Earth, we need an even higher temperature than inside the Sun, because we can't generate the same colossal pressure. At this temperature, no durable material can withstand it. The walls of any container would vaporize instantly. Therefore, physicists have had to resort to special magnetic traps called tokamak fusion reactors. They attempt to contain the scorching plasma within a powerful magnetic field, preventing it from ever touching the walls of the container. This sounds a bit like trying to hold a blob of molten lava with rubber bands, without ever being allowed to touch it directly with your hands. The blob would constantly try to slip out, contorting itself and escaping its confinement. To this day, we still spend more energy containing the plasma than the energy we get from the reaction itself. Nevertheless, progress is quietly being made every day. The International Fusion Project ITER in France is humanity's great hope for a clean, safe, and virtually limitless source of energy, because the fuel needed for this fusion reaction is an isotope of hydrogen, which we can easily extract from ordinary seawater. So far, we have journeyed from splitting the atom into a nucleus, to breaking that nucleus down into protons and neutrons. We have begun to understand how they interact and have learned where the immense energy of the stars comes from. It seemed as though we had reached the very bottom of matter. The foundation of the world, it seemed, had been found. However, in the 1960s, physicists were once again left stunned. It turned out that the proton was not a solid, indivisible marble. It, too, was made of something much smaller. And when we look deep inside a proton, we see a picture that completely shatters our common sense intuition. Deep inside, mass seems to be, quite literally, born from nothingness. In the mid-20th century, the world of elementary particles was like a bustling zoo where someone had accidentally left the gates open. Scientists kept building more and more powerful accelerators, smashing particles into each other head-on, only to discover an ever-increasing number of strange, new elementary particles. There were pions, kaons, lambda baryons, and sigma hyperons. There were so many, over 100 different types, that physicists had used up nearly all the letters of the Greek alphabet to name them. The physicist Enrico Fermi once joked, "If I could remember the names of all these particles, I would have been a botanist." The situation at the time was getting desperate. Nature surely couldn't be this complicated. The foundation of the entire universe couldn't possibly be made from hundreds of different building blocks. There had to be some system, some simpler structure that served as the source of everything. In 1964, two physicists, Murray Gell-Mann and George Zweig, independently proposed a groundbreaking solution. They suggested that all of these heavy particles, from protons and neutrons to their strange relatives, were not fundamental particles at all. In fact, they were composed of even smaller components. Gell-Mann named these tiny components quarks. He borrowed the name from a strange line in James Joyce's novel Finnegan's Wake. The name itself didn't have any particular meaning. It was just a strange new sound, and that was perfectly fitting for naming something entirely new in science. According to this quark theory, a proton consists of three quarks, two up quarks and one down quark. Similarly, a neutron also consists of three quarks, but in a different combination, one up quark and two down quarks. And the entire zoo of hundreds of other particles were just different combinations of these quarks and a few other types. Initially, many physicists considered this more of a mathematical trick than a physical reality. After all, no one had ever actually seen a quark. They never flew out during collision experiments. However, in the late 60s, at an accelerator at Stanford, they conducted an experiment similar to what Rutherford had done. The only difference was that, instead of using gold atoms, they targeted protons, and instead of alpha particles, they used super high-energy electrons. These electrons passed through the protons, but strangely, some of them were suddenly deflected back at very large angles. This proved that inside the proton, there were indeed tiny, incredibly hard particles. Quarks were real, and this is where the most astonishing part began to emerge. When scientists were able to estimate the mass of the quarks themselves, they were truly shocked. Let's take a look at these numbers. The mass of a proton is about 938 million electron volts. In the world of particle physics, mass is often measured in energy units for convenience. The mass of an up quark is only about 2 million electron volts, and the mass of a down quark is about 5 million electron volts. Now, let's try adding up the mass of 2 up quarks and 1 down quark. 2 plus 2 plus 5, the result is only 9. You see, this figure of 9 million electron volts compared to the actual mass of a proton, which is 938 million, is an enormous discrepancy. The total mass of the quarks accounts for only about 1% of the proton's entire mass. Imagine you go to buy 3 apples, each weighing only 100 grams. You put them in a bag, and then suddenly, that bag weighs 100 kilograms. That sounds absurd and crazy, doesn't it? So, where does the remaining 99% of our mass actually come from? What are we made of, if the most fundamental building blocks that make us up are nearly weightless? The answer to this question forces us to completely overturn all our old concepts about matter. The remaining 99% of a proton's mass is, in fact, pure energy. First, there is the kinetic energy of the quarks themselves. They are not sitting quietly inside the proton, but are constantly flying around in there at a speed nearly equal to the speed of light. They are confined within a breathtakingly small space, like flies trapped in a glass jar, and they are constantly slamming themselves against the walls of that prison. As Einstein pointed out, the energy of motion is equivalent to mass. The faster an object moves, the heavier it will appear to an outside observer. This frantic dance of the quarks creates a significant portion of the proton's weight. However, even that is not enough. The largest contribution to the actual mass comes from something that lies between the quarks. It is a force field called the gluon field. Quarks interact strongly with each other by exchanging intermediate particles called gluons. This name comes from an English word that means glue. Gluons are the particles that carry the strong interaction at the deepest level. Inside, a tiny proton is truly a screaming storm of energy. Quarks constantly toss gluons to each other. These gluons can, in turn, generate more gluons, and even create pairs of quarks and antiquarks, which then immediately vanish. A great ocean of energy is always seething in there, and it is this energy of the gluon field, the energy of that intense interaction, that creates the main mass of the proton. Just stop for a moment and think about this. Your entire body, this solid wooden table, or even our beloved planet Earth, 99% of all these things are not made of matter in our conventional understanding. In reality, we are made from the energy of force fields, where nearly weightless quark sparks are dancing ceaselessly. We are, in essence, condensed blocks of light and motion. Matter is no longer a static object. It is a dynamic process. It is a seething and never-ending interaction. However, another question arises. Why do the quarks have to move so fast? Why can't they fly out of the proton to be free? And why has humanity never been able to see a solitary quark in a free state? Here, one of the strangest mechanisms in nature is quietly at work, known as quark confinement. At this point, we have descended to a level where the familiar laws of everyday physics seem to be completely turned upside down. Imagine we are right inside a proton. Here, three quarks are performing their frantic dance amidst a vibrant ocean of gluons. Let's find out together how this magical glue works. In electromagnetism, forces usually weaken with distance. If you pull two magnets apart, they will gradually stop attracting each other. However, in the world of quarks, this rule is completely reversed. Imagine that the quarks are connected to each other by an invisible rubber band. That is the gluon tube. A super strong force field has been compressed into a bundle. As long as the quarks are close together inside the proton, they behave as if they are almost free. The rubber band is in a slack state. Physicists call this interesting phenomenon asymptotic freedom. The quarks just fly around, almost without paying any attention to each other. But now, try to pull one quark out. Try to rip it away from the proton it belongs to. As soon as you start pulling it, that invisible rubber band will begin to stretch. The farther you try to pull it, the stronger the force pulling the quark back becomes. That force doesn't weaken with distance. It remains extremely large, equivalent to about 14 tons of force. Just imagine, a force that could lift a large truck is hanging onto a particle so tiny it's unimaginable. That is the force holding the quark tightly inside its prison. As you put in more energy to try to pull it even farther, you are using your strength to stretch this gluon string. Energy is gradually stored inside the string, until at some point, when the tension reaches its limit, something incredible happens. That gluon rubber band will snap, but not in the way a normal string breaks. At the very point where it breaks, the accumulated energy has become so great that according to the formula E equals mc squared, it is sufficient to create two brand new particles from the vacuum, a quark and an antiquark. The newly created quark will immediately latch onto the broken end of the string to stay inside the old proton. Meanwhile, the new antiquark will bind to the quark you were trying so hard to pull out. The end result is that in your hand, you now have not a solitary quark, as you had hoped, but a new pair of particles. This pair is called a meson, which is the pion we talked about in earlier parts. And inside the proton, Everything remains as it was. Still, 3 quarks. You tried to separate one, but in the end, nature created new matter to fill that gap. That is the mechanism of confinement. Quarks seem to have been sentenced to life imprisonment forever. They can never exist alone as single particles. Mother Nature has issued a ban on naked color charges. Speaking of color, do you know why the theory of quarks is called quantum chromodynamics? The name comes from the Greek word chromos, which means color. Of course, our quarks are not actually painted with colors like red, green, or blue in reality. This is just a metaphorical comparison. While ordinary electric charge only has 2 types, positive and negative, the charge of a quark, also known as the strong charge, has 3 different types. Physicists have borrowed the names of the colors red, green, and blue to name them. The supreme law of nature has decreed that the universe must always be in a colorless or neutral white state. We never see objects with a single color charge. So how do we get this neutral white state? The first way is to mix all 3 colors, red, green, and blue, together. Protons and neutrons are constructed in exactly this way. Inside them, there is always a quark of each of the aforementioned colors. When combined, they create a neutral white charge. The second way is to mix a color with its own anticolor, such as red combined with anti-red. Mesons are constructed based on this principle. In this fantastical world, the gluon acts as the color-transmitting particle. Every time a quark emits a gluon, it immediately changes its own color. For example, a red quark emits a red anti-blue gluon and instantly becomes blue. This gluon flies to another blue quark, which absorbs it and in turn transforms into a red one. Those colors are constantly flickering, changing, and swapping with each other inside the proton. It's really like a fantastical dance floor with dazzling colored lights. This world of quantum chromodynamics seems incredibly strange and incomprehensible to our daily lives. However, it is precisely the strange properties of that gluon vacuum that determine the mass of your body and mine. We are, in fact, byproducts of the magical interaction of colors silently taking place in the darkness of the microworld. Those brilliant colors are constantly flickering and changing inside the proton. It's truly like a fantastical dance floor with enchanting colored lights. This world of quantum chromodynamics seems incredibly distant from our daily lives. But, you know, it is the strange properties of that very gluon vacuum that determine the mass of our own bodies. We are, in reality, just byproducts of the interaction of colors silently taking place in the darkness of the microworld. But if the strong force is so powerful and permanent, why does anything change at all? Why do phenomena like radioactive decay exist? And why can a neutron turn into a proton? This is where another player quietly enters the game, one that acts in absolute stealth. It is a force much weaker than electromagnetism, but it possesses a unique ability. It can change the very nature of particles. It is the true alchemist of the subatomic world. Scientists call it the weak nuclear interaction. The name weak can be misleading. It's true that in terms of pure strength, it is inferior to the electromagnetic interaction and pales in comparison to the strong force. However, its influence on the fate of the entire universe is immense. If the strong force is responsible for keeping matter stable, then the weak force is responsible for allowing matter to change and transform. Think back to the proton-proton chain inside the sun that we talked about in earlier sections. 2 protons fuse, and then one of them transforms into a neutron. But how can a proton turn itself into a neutron? Aren't they completely different particles? The strong force cannot change one type of quark into another, and neither can the electromagnetic force. Only the weak interaction holds the exclusive license for this magical transformation. It has the ability to change the flavor of quarks. Yes, Physicists often use the term flavor to refer to different types of quarks, such as up, down, or strange. Let's take a look at how this happens under an imaginary microscope. A neutron consists of one up quark and two down quarks. Meanwhile, a proton consists of two up quarks and one down quark. For a neutron to become a proton, one of its down quarks must transform into an up quark. At a certain moment, this down quark will emit a very heavy force-carrying particle called a W boson. Immediately after emitting this boson, the quark has completely changed its identity. It has gone from being a down quark to an up quark. And just like that, the neutron has officially turned into a proton. So what happened to that W boson? It exists for only an extremely brief period, just a tiny fraction of a moment. It almost instantly decays into an electron and another mysterious particle called a neutrino. This transformation process is called beta decay. It's what happens inside nuclear reactors and in radioactive waste. And it's also what makes a Geiger counter tick. The weak interaction is the deep origin of natural radioactivity. In this story, the role of the neutrino is truly worth its own mention. In the early years of the 20th century, when physicists were studying beta decay, they observed a very strange picture. A neutron turned into a proton and emitted an electron. However, when they measured the energy of the fragments, they got a different number every time. It seemed as if some of the energy had vanished into thin air. This was so serious that the scientist Niels Bohr was even willing to sacrifice the sacred law of conservation of energy. But Wolfgang Pauli, who was considered the conscience of physics, bravely said his famous no. He argued that there must be another particle present, an invisible culprit, a tiny thief that had quietly carried that energy away. This particle has no electric charge and almost never interacts with ordinary matter. Pauli called it the little neutral one, but Enrico Fermi later renamed it the neutrino, which means tiny neutral one in Italian. Pauli once bet a case of champagne that the neutrino would never be discovered, and he ultimately lost that bet. 25 years later, the neutrino was officially captured experimentally. Neutrinos are truly the ghosts of the universe. Every single second, 60 billion neutrinos born from the sun's core are passing through your thumbnail. They fly through the entire Earth as easily as if they were passing through empty space. To be certain of capturing just a single neutrino, you would need a wall of lead that is 1 light-year thick. The weak interaction is the only force, besides gravity, that these ghostly neutrinos can feel. However, the weak interaction has another shocking characteristic. It breaks symmetry. Imagine looking at yourself in a mirror. You raise your right hand, and your reflection in the mirror raises its left hand. The world inside the mirror looks just as plausible as our real world. The laws of physics should work exactly the same for us and for the world in the mirror. Gravity doesn't care if a rock is flying to the left or to the right, and neither does electromagnetism. For a long time, physicists held an absolute belief that nature was perfectly symmetrical. This principle is called the conservation of parity. However, in 1956, 2 young theorists, Tsung-Dao Lee and Chen-Ning Yang, began to suspect that something was wrong. They proposed that the weak interaction could distinguish between left and right. To test this hypothesis, the brilliant experimentalist Chien-Shiung Wu conducted an incredibly meticulous experiment. She took cobalt-60 nuclei, cooled them to near absolute zero, and placed them inside a strong magnetic field. The purpose was to make all these nuclei align their spin axes in a single direction. Cobalt-60 is radioactive. It decays and emits electrons. If the world were truly symmetrical, the electrons should have flown out equally in both directions, both up and down along the axis of spin, like water droplets flinging off a spinning wheel. However, what Wu witnessed was something completely different. The vast majority of electrons flew out in only one direction. opposite to the direction of the spin. It was a huge shock to the scientific community. Imagine spinning a top, but it only kicks up dust downwards, never upwards. This proved that our universe has a preference. At the most fundamental level of the weak interaction, our world is essentially left-handed. All neutrinos in the universe always spin to the left, like a screw with a left-handed thread. Right-spinning neutrinos simply do not seem to exist. This shocking discovery completely shattered the perfect picture of a symmetrical world that humanity had always believed in. The weak interaction turned out to be not just a force, but a strange and somewhat skewed mechanism embedded deep within the very fabric of reality. It is thanks to this strange force that our sun has been able to burn steadily and stably for billions of years. The process of transforming a proton into a neutron via the weak interaction happens very slowly. This is the bottleneck of the entire fusion reaction. If the weak interaction were just a little bit stronger, our sun would have burned through all its fuel in just a few short years and exploded like a supernova. Conversely, if it were any weaker, the sun would never have been able to ignite. The fact that we live peacefully today is actually thanks to this miraculous weakness. However, we still have one extremely important question left unanswered. We said that the W bosons, the particles that carry the weak force, are very heavy. They are about 80 times heavier than a proton. It is because of this weight that this force has a very short range, because it's very difficult to throw such a heavy ball very far. But where did they get that enormous mass? And where do electrons, or even the quarks themselves, get their mass, when they are bare quarks without a surrounding cloud of gluons? We've understood that 99% of a proton's mass is the energy of the gluon field, but the remaining 1% of mass from the fundamental particles remains a great puzzle. Why is the photon the particle of light completely massless and able to fly forever through space? Meanwhile, the W boson is as heavy as an entire krypton atom and vanishes instantly. The answer to this difficult question was found in the 60s, and it required the introduction of a new field of force, a field that fills the entire vast universe, yet one whose presence we don't notice until we try to create disturbances in it. This is the Higgs field. Let's conduct a thought experiment. Imagine a vast, endless party hall filled with people. This is a party crowded with journalists and photographers. They are distributed evenly throughout the hall, chatting animatedly with each other. This is the symbolic image of the Higgs field. It is present everywhere, permeating every corner of space, even in the deepest vacuum. Now, imagine an ordinary, unknown person walking into that hall. He could calmly walk through the crowd to the other side without anyone noticing or stopping him. He moves lightly and extremely quickly. This person is an analogy for a photon. A photon does not interact with the Higgs field. It feels no resistance, so it has absolutely no mass and always travels at the speed of light. Now, imagine a world-famous movie star walking into that same room. As soon as she appears, journalists would immediately surround her. A dense crowd forms around this celebrity. They bombard her with questions and ask for autographs. The star would find it very difficult to move. She has to slowly weave her way through the crowd. Every step she takes requires a lot of effort. If she stops, the crowd will continue to surround her without letting up. It is this crowd clinging to the star that gives her something called inertia. It's very difficult for her to speed up, and it's also very difficult for her to slow down. This star is an analogy for a particle that has mass, such as an electron or a quark. They interact very strongly with the Higgs field and get bogged down in it. And this viscous drag of space is what we perceive as mass. Mass is not actually an intrinsic property of a particle. Mass is a measure of how tightly a particle is clinging to the Higgs field. If we could turn off the Higgs field throughout the entire universe with a snap of our fingers, then immediately all particles would completely lose their mass. Electrons, quarks, and W bosons would all become weightless and zip away at the speed of light. At that moment, atoms would immediately disintegrate because massless electrons could no longer hold themselves in their orbits. All of us would instantly vanish into nothingness. This brilliant idea was proposed by the British physicist Peter Higgs and several colleagues in 1964. This theory is truly beautiful. It saved the entire standard model of physics by explaining why the W boson is heavy while the photon is light. This is called spontaneous electroweak symmetry breaking. However, a theory, no matter how beautiful, must be proven by reality. How can we detect a force field that is everywhere but completely invisible? The only way is to create a powerful disturbance within that very field. Let's go back to our hall full of journalists. Imagine there are no stars this time, but suddenly someone starts a rumor at one end of the hall. The journalists hear the rumor and immediately gather into a crowd to buzz about it. Then, this group passes the rumor on even further. Now, a condensed wave of the crowd is spreading across the hall. This clump in the force field, this concentrated wave, is in fact the Higgs boson. If we can capture the Higgs boson, we will officially prove that this force field truly exists. However, to disturb this invisible ocean, to create such a wave, we need to act upon the vacuum with an enormous amount of energy. A condensed wave of the crowd spreads across the room. This clump in the force field, that concentrated wave, is in fact the Higgs boson, the very particle we have been searching for. If we can capture the Higgs boson, we will officially prove that this force field truly exists. But to disturb this invisible ocean, to create such a wave, we need to act upon the vacuum with an enormous amount of energy. For this grand purpose, humanity came together to build the greatest machine in all of history, the Large Hadron Collider, also known as the LHC. It is a giant 27-kilometer circle deep underground, running along the border of France and Switzerland. Inside this magnificent ring, thousands of superconducting magnets are accelerating protons to a speed just a few meters per second, slower than the speed of light. Two beams of protons are fired in opposite directions and collide head-on inside special detectors. The energy of the collision is so great that it can recreate the conditions that existed in the universe just a tiny fraction of a second after the Big Bang. Inside this energetic fireball, particles that do not exist in our ordinary, everyday world were born. The hunt for the Higgs boson had dragged on for decades. This was perhaps the most complex and arduous task in the entire history of experimental physics. The Higgs boson exists for an extremely short period of time, only about a millionth of a billionth of a billionth of a billionth of a second. It immediately decays into other types of particles. Scientists had to patiently sift through trillions of collisions to find the characteristic decay traces, the fingerprints that could indicate the presence of the Higgs particle. And then, on July 4th, 2012, the whole world held its breath. At CERN, the European Organization for Nuclear Research, a historic press conference took place. In the auditorium that day sat an elderly Peter Higgs himself, with tears welling in his eyes. The scientists announced boldly to humanity, "We have found a new particle, fully consistent with the Higgs boson." It was truly a resounding victory. The final brick of the standard model had officially been found. We had confirmed that emptiness is not actually empty at all. It is filled with an invisible substance that is silently giving mass to everything in the universe. However, this very discovery also gave rise to new, perplexing questions. The mass of the Higgs boson turned out to be a bit strange. It's about 125 giga-electron volts. This number is not too large, but also not too small. It seems to lie in a region of instability. This has led some physicists to hypothesize that our vacuum might just be a false vacuum. They fear that one day the Higgs field could suddenly transition to another state, completely changing the laws of physics throughout the entire universe. But don't you worry, that's just an interesting topic for science fiction horror movies, not something that will happen in the near future. The probability of this is truly extremely, extremely small. What's more important is that we now understand that the vacuum is not just simply nothing. In fact, it is an extremely complex, dynamic environment. In that space, there are always gluon fields, the Higgs field, and the fields of all other fundamental particles. If we look at the vacuum through the lens of quantum mechanics, we will see a picture that is far more insane and fantastical. Even if we remove all particles, turn off all light sources, and cool everything down to absolute zero, there is still energy in that emptiness. The vacuum is always seething. In it, virtual particles are constantly being born and then disappearing. It's like an entity breathing with a steady rhythm. In classical physics, the vacuum is like a stage from which all actors and decorations have been cleared away. It is an empty, quiet, and somewhat boring place. It is the number zero, with absolutely nothing in existence. However, quantum mechanics is a science that absolutely does not accept neat, round zeros. One of the most fundamental principles of the quantum world is the Heisenberg uncertainty principle. This principle states that we can never know with perfect accuracy both of certain quantities at the same time, such as a particle's position and velocity. But there is another pair of quantities that is bound in the same way: energy and time. The uncertainty principle for energy and time shows that, for an extremely short period of time, the law of conservation of energy can be temporarily violated. Nature seems to allow you to borrow energy from nothingness, with the single condition that you must pay it back very quickly. The more energy you borrow, the faster you have to return it. This means that the vacuum cannot be completely empty with an absolute energy level of zero, because an energy level of zero and an infinite amount of time are parameters that are too precise, something Heisenberg's principle forbids. Therefore, within the vacuum, energy fluctuations are constantly occurring. Right now, right in front of your nose, in that seemingly empty space, every fraction of a second, pairs of particles are emerging from nothingness. They are electrons and positrons, quarks and antiquarks, or photons and antiphotons. They appear, exist for a fleeting moment, then annihilate each other and disappear to repay the borrowed energy. We call them virtual particles. But my friend, don't let the word virtual fool you, because their effect on reality is completely real. The vacuum is not a flat, silent lake, but it is truly a seething cauldron, a foam of matter that is constantly being born and dying. It might sound like science fiction, but we actually have solid evidence. One of the most beautiful and compelling pieces of proof is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted an astonishing phenomenon. If you take two perfectly polished metal plates and place them in a vacuum extremely close to each other, less than a millionth of a meter apart, they will, strangely, pull toward each other automatically. No electricity, no magnets, and no gravity are needed. The emptiness itself pushes them together. How is this possible? Imagine that the vacuum is filled with the wavelengths of virtual photons. Between the two metal plates is an incredibly narrow space. The long wavelengths simply can't fit in there. Only short, small wavelengths can exist in that space. Meanwhile, outside the plates, in the vast open space, all kinds of wavelengths can exist, from short to long, and even giant ones. The result is a pressure imbalance. There are more waves on the outside than on the inside. The pressure from the virtual particles on the outside pushing on the plates is much stronger than the pressure from the inside. It's the vacuum on the outside that pushes harder, squeezing the two plates together. This magical effect has been precisely measured experimentally, and it perfectly matches what the theory predicted. We have literally measured the pressure of nothingness. Another solid piece of evidence is the Lamb shift, which occurs inside the hydrogen atom. The energy levels of the electron in the atom are shifted ever so slightly compared to the original calculations. This happens because the seething vacuum surrounding the electron affects it. The silent noise of the vacuum gently nudges the electron. Therefore, when we speak of emptiness, we are actually talking about an incredibly complex physical environment that contains a vast amount of energy. And this is where physicists face the biggest problem in modern science. If the vacuum is truly full of energy, then according to Einstein, this energy must have mass, and mass must certainly create gravity. Scientists have tried to calculate how much this emptiness actually weighs. They summed up the contributions of all possible virtual particles and arrived at a number. It was a colossal number, unimaginably large. If the vacuum truly possessed such an energy density, our entire universe should have immediately collapsed into a giant black hole or been torn apart right after it was born. And yet, the reality is that when we look up at the magical night sky, we see that the universe is still expanding. Furthermore, as discovered in the late 90s, the universe is not just expanding normally, it's expanding at an accelerating rate. Some mysterious force is actively pushing the galaxies away from each other. Scientists call this force dark energy. Many physicists believe that dark energy is, in fact, the energy of the vacuum. However, there is a huge catch here. The observed value of dark energy is 10 to the power of 120 times smaller than what quantum field theory predicted. That's the number 1, followed by 120 zeros. This is truly the biggest and most shocking mistake in the entire history of theoretical physics. This terrifying discrepancy is a catastrophe for human knowledge. We know for sure that vacuum energy exists because of the Casimir effect. We also know that it's directly affecting the universe, causing its accelerated expansion. Yet, our greatest theories, which work perfectly for atoms and quarks, completely collapse when we try to apply them to explain the energy of emptiness. This serves as a reminder that the journey into the nature of matter is far from over. We've found the atom, the nucleus, quarks, gluons, and the Higgs boson. We've understood where 99% of our mass comes from. But now, we are slamming into a wall of ignorance about the very magical fabric of space-time. In the final chapter of this journey, we will summarize this entire grand investigation and try to look further toward the horizon. What other mysteries is nature still hiding from us? And what is our true place in this world of incessantly seething fields and energies? We've traveled a long and emotional road together. We started with the most ordinary everyday things, from a wooden table and a chair to a delicate golden leaf. And then, step by step, we went down the rabbit hole into the enchanting quantum reality. We have come to understand that the solidity of all things is just an illusion created by electromagnetic fields. Together, we've split the nucleus into protons and neutrons, witnessed the brilliant dance of quarks and gluons, felt the silent breath of the vacuum, and touched the mysterious Higgs field. It seems that, by now, we've grasped everything. We have the Standard Model, one of the greatest achievements of modern physics. We know all the bricks that build this world and understand all the forces that govern this magnificent assembly. Perhaps we could breathe a sigh of relief, close our textbooks, and confidently say, we have understood the entire universe. However, in this final chapter, I must disappoint you a little, or perhaps give you a new source of inspiration. Because everything we have diligently discussed over the past 11 chapters, from tiny atoms, brilliant stars, and distant galaxies, to vast clouds of gas, and even you, me, and all the modern devices around us, all of it actually makes up only a tiny, pitifully small fraction of reality. Prepare yourself for the most powerful shock to our human ego since the time of the astronomer Copernicus. All the ordinary matter that we have painstakingly studied for so long actually makes up a mere 5% of the total composition of the universe. Only 5%. Just imagine it's like you've just bought a huge, magnificent house, but you're only allowed to live in a tiny, cramped closet under the stairs. All the other vast rooms are locked tight, and you can't even see what's inside them. You can only hear strange, mysterious sounds echoing from behind those sealed walls. The remaining 95% of the entire vast universe is darkness, dark matter, and dark energy. These are the two great unknowns that are silently directing the fate of the entire universe, while we are still busy fumbling around with our tiny quarks. Let's start by learning about dark matter. How could humans know of its existence if it's completely invisible? This dramatic story began in the 1930s, but it truly made a huge splash in the 70s thanks to the work of the brilliant astronomer Vera Rubin. She dedicated her efforts to studying the rotation of spiral galaxies, which have a structure similar to our own Milky Way. Basically, a galaxy is like a giant carousel in space, where billions of stars are spinning around a center. We are very familiar with the laws of gravity from Newton and Kepler. These laws work perfectly within our solar system. The farther a planet is from the Sun, the slower it orbits. Mercury, being close, zips around like crazy, while Neptune, far away, crawls along at an incredibly slow pace. This makes perfect sense, because gravity naturally gets weaker with distance. Therefore, to stay in orbit, a distant planet doesn't need a very high speed. Vera Rubin expected to see the same thing happening inside galaxies. Stars on the outer edges of the galactic disk should be moving slowly. Otherwise, they would be flung out into the vastness of intergalactic space. This is because the gravitational pull of the visible stars and gas clouds at the center is simply not strong enough to hold on to the stars at the edge if they move too fast. But when Vera Rubin started plotting the velocity curves, she couldn't believe her own eyes. The velocity curves were all flat. The stars at the very farthest edge of the galaxy were racing along at the same frantic speed as the stars closer to the center. According to the normal laws of physics, this should be absolutely impossible. With the amount of mass we can see, including the glowing stars and gas clouds, the galaxies should have flown apart immediately, like wet pieces of toilet paper being blown away by a fan. The stars should have flown apart into space billions of years ago, yet galaxies have always remained stable and intact. This can only mean one thing, that we are completely missing something incredibly important. Inside every galaxy, there must exist a hidden mass, a huge amount of invisible matter, creating an extremely powerful, additional gravitational force. The gravitational force from the visible stars and gas clouds we see in the galactic center is simply not strong enough to hold onto the stars on the distant outer edges, which are moving at very high speeds. Yet, when astronomer Vera Rubin plotted their velocity curve, she couldn't believe her own eyes. Those velocity curves were completely flat. The stars at the very edge of the galaxy were racing along at the same frantic speed as the stars near the center. This is something that should be logically impossible. With the amount of mass we can see, consisting of luminous stars and gas lanes, galaxies should have disintegrated instantly, like pieces of wet toilet paper being blown apart by a fan. The stars should have scattered into space billions of years ago. Yet galaxies have always remained stable and have held together. This can only mean one thing. We are completely missing something incredibly important. Inside every galaxy, there must be a hidden mass, an enormous amount of invisible matter, creating an extremely powerful, additional gravitational force. This gravity acts silently like a kind of cosmic cement, keeping fast-moving stars in their proper orbits. And this hidden mass must be astonishingly large, about 5 times the entire amount of matter we can see. We call it dark matter. However, the word dark here isn't entirely accurate. Coal is also dark, but it still reflects or absorbs light. Dark matter, on the other hand, is completely transparent. It doesn't emit light, it doesn't reflect it, and it doesn't absorb any light rays at all. Light passes right through it, as gently as if passing through a mysterious ghost. It doesn't participate in the electromagnetic interaction, and it doesn't interact with anything else, except for gravity. Just imagine, countless dark matter particles are flying through your body right at this very moment, but you don't feel a thing because they don't collide with the atoms that make you up. What dark matter actually is, to this day, humanity still doesn't know for sure. Scientists are still tirelessly developing different theories. Perhaps they are weakly interacting massive particles, or perhaps they are axions. To try and capture them, people have painstakingly built enormous detectors deep underground, in mines filled with xenon or argon gas. We are still patiently waiting for the moment when at least one dark matter particle happens to collide with the nucleus of an ordinary matter atom. So far, everything has been completely silent. But if dark matter is like the cement that binds the universe together, then dark energy is the complete opposite. It's like a powerful explosive that is trying to rip this universe to shreds. The discovery of dark energy happened quite recently, in 1998. At that time, two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, decided to take measurements to see how the expansion of the universe was slowing down. Everyone at the time was certain that the expansion was gradually slowing, because the universe is full of mass, including both ordinary matter and dark matter. And mass always creates gravity, and gravity is an attractive force. It should be pulling galaxies closer together, slowing down their dispersal after the great push from the Big Bang. The only question at the time was how fast this breaking process was happening, and whether the universe would ever stop completely and begin to contract. To find the answer, the astronomers used a special type of supernova for measurement, called a Type 1a. These are explosions of white dwarf stars, which always occur at a certain mass, and therefore, they always have the same brightness. They are like the standard candles of the entire universe. If you see such a candle becoming dimmer, you know exactly how far away it is from us. However, after measuring the distance to distant supernovae and the speed at which they were moving away, the scientists got a result that made them think their equipment had failed. The universe wasn't slowing down as predicted. On the contrary, it was accelerating. Galaxies are flying away from each other faster than ever before. There is some mysterious force that is actively pushing space itself apart. That force is fighting against gravity, and it seems to be winning. This powerful force is called dark energy, and if dark matter makes up about 27% of the universe, dark energy makes up a whopping 68%. Remember what we talked about regarding the vacuum. Most physicists are leaning toward the theory that dark energy is the energy of space itself, the energy of the vacuum. This has a truly terrifying implication. That emptiness not only contains energy, but it also possesses something called negative pressure. As the universe gets bigger, there is more space, and therefore more dark energy within it, which pushes the universe to expand even more forcefully. It is a self-perpetuating and unstoppable process. What does this mean for our distant future? If this acceleration continues, then in hundreds of billions of years, galaxies will be so far apart that even their light will no longer be able to reach us. The night sky, then, will become pitch black, silent, and incredibly empty. Our Milky Way will be left all alone in the void. And then, perhaps dark energy will tear apart our galaxy itself, tear apart solar systems, and even rip atoms to shreds. This haunting scenario is known to scientists as the Big Rip. So, what are we left with? Try to imagine a pie chart. One huge slice, taking up nearly 70%, is dark energy, something whose true nature we still don't understand at all. Another quarter of the pie, about 25%, is dark matter, those ghostly, invisible particles that we also don't really know what they are, and we are left with just a thin, fragile sliver, a mere 5%, which is the protons, neutrons, and electrons. That is the sparkling stars, the planets, the lanes of gas, and faint dust. And that is also us. We are essentially tiny specks of foam on the crest of a wave in a vast, dark ocean. We are a rare exception, a miraculous anomaly. We are a tiny island of light, floating in an immense sea of darkness. But my friend, please don't rush to feel despair because of our own smallness. Instead, try to look at this from a more positive perspective. Only this 5% of ordinary matter possesses a very unique characteristic, which is that it has the miraculous ability to self-organize. Quarks gather to form protons, and protons form nuclei. Nuclei capture electrons to create the first atoms. Then atoms link up to form molecules, and molecules twist together to form the DNA, double helix of life. From the primordial chaos of the Big Bang, and from the cold ashes of distant stars, an extraordinary type of matter was born. Matter that can think, that can feel, and that knows how to ask questions about its own origins. We began our story tonight with a question. Where does the energy inside an atom truly come from? And then we found our answer. That energy is an echo from the dawn of the universe, the energy of gluon fields, the energy of strong nuclear bonds. They are all great forces that have been perfectly preserved from the first moments of creation. Every single atom currently in your body, with the exception of hydrogen, was once forged inside the blazing nuclear furnace of a dying star. The carbon in your muscles, the iron in your flowing blood, the calcium in your bones, or the oxygen in our lungs. All of it is stardust. We are the nuclear waste of the universe, but have been fortunate enough to gain consciousness and a soul, and with that miraculous consciousness, even though we sit on a tiny planet next to an ordinary star, we can still use our minds to comprehend the deepest levels of creation. Although we cannot see quarks with the naked eye, we still understand their properties. Though we don't feel the curvature of space-time, we predicted the existence of black holes and gravitational waves, and then actually found them. We've learned how to ignite a sun right here on Earth, and found ways to treat diseases with beams of protons. Of course, the path ahead is still filled with mystery. Physicists have always dreamed of a great theory of everything, one that could unite both gravity and quantum mechanics. Right now, these two theories don't seem to get along, like two neighbors speaking completely different languages. Perhaps the final solution lies in string theory, a theory suggesting that all particles are not tiny points, but minuscule strings vibrating in 10-dimensional space. Or maybe it's loop quantum gravity, or perhaps it will be something entirely new, just now beginning to sprout in the mind of some young person. Science isn't a rigid, unchanging set of rules. It's a living, dynamic, and continuous process. The frontier of knowledge is always expanding, revealing new horizons of our own ignorance. And that is a truly wonderful thing, because mystery itself is the endless fuel for our intellect. Inside one tiny atom, there is truly an abyss of energy. But there is a far greater power lurking in human curiosity itself, the very power that drives us to relentlessly explore that abyss. Thank you for joining me on this long and fascinating journey, from the solidity of a wooden table to the vibrant activity of a vacuum, from the first speculations of the ancient Greeks to the deep mysteries of dark energy. This world is truly more complex, stranger, and more incredible than we ever imagined. And I am certain of one thing: humanity's most exciting discovery still lies ahead. Try to look deeply into that silent space. It is not empty at all. It holds countless wondrous possibilities,